Picture a 5-ton block of iron suspended above your head. It hangs from a piston inside a steam cylinder, the height of a 2-story building, and the man standing at the controls can bring that block down with enough force to flatten a white-hot steel bar into a perfect sheet in a single stroke. The impact sends vibrations through the factory floor, through the foundations, through the ground itself, until housewives a quarter-mile away feel their cupboards rattle. That same machine, in the hands of that same operator, can descend with such delicate precision that it cracks the shell of an egg sitting inside a wine glass and leaves the glass completely untouched. What nobody knew in 1839, when a Scottish engineer first sketched this machine in his notebook, was that this single invention would make it possible to build the ships, the railways, the bridges, and the weapons that turned a small island nation into the most industrialized country on Earth. This is the story of the steam hammer, and it starts in the last place you would expect. It was 1816, and a boy named James Nasmyth was making a mess of his father's studio in Edinburgh. Alexander Nasmyth was a well-known landscape and portrait painter. He had clients, commissions, a reputation to maintain. But Alexander had a secret obsession that had nothing to do with canvas and oil. He kept a forge in the family home. A working forge with tools and scrap metal and fire right there alongside the easels and the paintings. And his youngest son James could not stay away from it. By the time he was a teenager, James had already built small working models of steam engines in that home workshop. He was obsessed with how things moved, how metal bent, how pressure and heat could be controlled. The paintings on the walls meant nothing to him. The forge was everything. His father recognized what he was looking at. This was not a boy who would become an artist. So Alexander connected his son with people in the engineering world. And by the time James turned 19, he had landed the most valuable apprenticeship in Britain. He went to work for Henry Maudslay in London. Maudslay was already a legend. He had invented the metal precision lathe, built the block-making machinery for the Royal Navy's Portsmouth dockyard, and his workshop on Westminster Bridge Road was the place where any serious young engineer in Britain wanted to train. Nasmyth learned everything the old master could teach him, not just how to cut metal, but how to think about the relationship between force and control. How a tiny adjustment in the setup of a tool could mean the difference between a clean cut and a ruined workpiece. How precision was not the absence of power, but the discipline applied to it. Those 2 years shaped everything that came after. When Maudslay died in 1831, Nasmyth had already absorbed enough knowledge to launch his own career. He started small, renting a room above a glasscutter's workshop in Manchester, where he began building machine tools on his own. That arrangement ended abruptly when a heavy engine beam he was working on crashed through the floor into the business below. Nasmyth needed a proper factory, and he needed one fast. He partnered with a businessman named Holbrook Gaskell, and together they opened a foundry in August of 1836. Nasmyth chose the location with the same care he applied to his engineering. He picked a spot in Patricroft, on the western edge of Manchester, right where the Bridgewater Canal crossed the newly opened Liverpool and Manchester Railway. Canal, railway, and road, all converging at one point. He could ship heavy machinery anywhere in Britain from that single location. He named it the Bridgewater Foundry, after the canal duke who had first connected Manchester to the wider world by water. Within a few years, the foundry had grown into one of the busiest machine shops in England. Nasmyth was building steam locomotives, 20 of them for Brunel's Great Western Railway alone, along with precision machine tools, pumps, and hydraulic presses. He employed over 400 workers. Business was good, but the job that changed everything came not from a customer walking through his door. It came from a letter. In 1839, Isambard Kingdom Brunel was in the middle of building the most ambitious ship the world had ever seen. The SS Great Britain was going to be the first large iron-hulled steamship, and in its original design, it relied on enormous paddle wheels for propulsion. Those paddle wheels needed a drive shaft, and Brunel's engineers had calculated that the shaft would need to be about 30 inches in diameter. 30 inches of solid forged iron, shaped with enough precision to spin at high speed without wobbling or cracking. The problem was simple and devastating. There was no forge in Britain or anywhere else in the world that could produce a piece of metal that large. The biggest tilt hammers and trip hammers of the day were human-scale tools. They could shape horseshoes and axle heads and small engine parts, but a 30-inch shaft for an ocean-going steamship was something else entirely. The existing technology simply could not do it. Brunel wrote to his friend Nasmyth. He explained the problem. He asked if there was any possible solution. Nasmyth thought about it, and on the 24th of November, 1839, he opened his scheme book and drew a sketch. It was a simple drawing, almost deceptively simple. An anvil at the bottom to hold the workpiece, a large block of iron above it, attached to a piston rod, an inverted steam cylinder above that. The idea was that steam would be pumped into the lower part of the cylinder to raise the block, and then, when the steam was released, the block would fall under gravity onto the metal below. That was the single-acting version. Later improvements added what engineers called double-acting capability, where steam was also injected above the piston to actively push the hammer down, adding the force of steam pressure on top of gravity for a far more devastating blow. But the real genius of the concept was not raw power, it was control. The operator could adjust exactly how much steam went into the cylinder, and therefore exactly how high the block was raised, and therefore exactly how hard it came down. A slight tap or a building-shaking strike, all from the same machine, all managed by one person standing at a valve. Nasmyth's foundry manager, a man named Robert Wilson, later added a self-acting mechanism that made the control even finer. The metal to be worked sat on an anvil block with an adjustable plate that could be changed out to give the pressed metal whatever shape was needed. And because the hammer followed vertical guides on its descent, it hit the same spot every single time. You could forge 100 identical components, one after another, each bent to the same exact angle. Before the steam hammer, that kind of repeatability was impossible. It was an elegant solution, and it sat in his notebook for a while, because, as it turned out, Brunel changed the design of the Great Britain. Instead of paddle wheels, the ship would use a screw propeller, which needed a much smaller shaft. The urgent demand for the giant hammer disappeared, at least for the moment. Nasmyth filed the sketch away, but here is the detail that everyone missed at the time. Across the English Channel, at an ironworks in the French town of Creusot, another engineer was thinking about exactly the same problem. François Bourdon was the chief engineer at the Schneider Works. The Schneider brothers had bought a rundown ironworks in Burgundy and were turning it into a major industrial operation. Bourdon had experience building steamships in both the United States and England, and he understood the same bottleneck that Nasmyth had identified. The forging tools of the 1830s simply could not keep up with the size of the things that industry now needed to build. Ships were getting bigger, locomotives were getting heavier, cannon barrels were getting longer, and the hammers that shaped the metal for all of these things had barely changed in centuries. So Bourdon designed his own version of a steam-powered hammer, and unlike Nasmyth, Bourdon actually built it. In 1840, the first working steam hammer in the world was assembled at Creusot. It weighed about 2,500 kilograms and could lift its striking head to a height of 2 meters. It was not enormous by later standards, but it worked. It forged parts for the steamships Bourdon was building for river and transatlantic service, components that no other tool in France could have produced. The success of this machine gave the Schneider factories an immediate competitive edge over every other ironworks in the country. Bourdon filed a patent in September of 1841, and Schneider brothers took out the definitive patent in April of 1842. Now, Nasmyth's sketch had been sitting in his notebook for over 2 years at this point, and in April of 1842, Nasmyth visited the Schneider works at Creusot. He saw Bourdon's hammer in operation. He went home to Manchester and built his own steam hammer later that same year. In 1843, a bitter dispute erupted between the two men over who had truly invented the machine. Bourdon had built the first working model. Nasmyth claimed the original concept was his, and that Bourdon had somehow seen his sketch and copied the idea. The argument was never fully resolved, and depending on whether you read British or French accounts, you will get a very different answer about who deserves the credit. What is not disputed is that both men arrived at the same idea independently, driven by the same industrial need, at almost exactly the same time. That happens more often in the history of invention than most people realize. What Nasmyth did next, though, was something Bourdon never matched. Nasmyth was a showman. He understood that an invention is only as good as the story you tell about it, and he told a story that spread across Britain in a matter of months. The most famous demonstration happened in front of the Lords of the Admiralty, who had placed an order for one of Nasmyth's hammers. Nasmyth placed an egg inside a wineglass and positioned both on the anvil directly beneath the hammerhead. The block weighed about 2.5 tons. The Navy officials in the room must have thought the man was out of his mind. But Nasmyth opened the steam valve, raised the block, and brought it down with such controlled precision that the eggshell cracked cleanly, while the wine glass beneath it was not even chipped. Then, before anyone had finished processing what they had just seen, he cranked the valve wide open and brought the full weight of the hammer down on a bar of hot iron. The blow shook the building from floor to roof. Crockery rattled in homes a quarter-mile away. The same machine, the same operator, the difference between a feather touch and an earthquake, controlled by a single valve. That demonstration did more for Nasmyth's business than any patent filing ever could. Orders poured into the Bridgewater Foundry from shipbuilders, railway companies, and manufacturers across Europe. The steam hammer allowed the production of larger and stronger forgings than had ever been possible before. It tightened the molecular bonds in metal, made iron and steel denser and more uniform, and could shape components for boiler engines, locomotive axles, anchor chains, and ship hulls that would have taken teams of men with hand hammers days or weeks to produce. By 1843, Nasmyth had improved the original design by injecting steam above the piston as well as below, giving the double-acting hammer even greater striking force on the downstroke. The steam hammer was no longer a curiosity. It was the tool that serious industry could not function without. And Nasmyth was not finished inventing. In 1843, he adapted the hammer principle into a pile-driving machine, using a 4-ton hammer block that could deliver 80 blows per minute. The first public trial took place on the 3rd of July, 1845, at the Royal Dockyards in Devonport. His machine drove a 70-foot timber pile into the ground in 4.5 minutes. A crew using the conventional method, the hand-operated drop hammers that had been standard for centuries, took 12 hours to drive an identical pile into the ground nearby. 4.5 minutes versus 12 hours. That is not an incremental improvement. That is a complete replacement of everything that came before it. If Nasmyth had stopped there, this would already be one of the great engineering stories of the 19th century. But he did not stop there, and neither did anyone else. Because the steam hammer had started an arms race, and the stakes kept climbing. In 1861, Alfred Krupp's steelworks in Essen, Germany, unveiled a new steam hammer that dwarfed anything Nasmyth or Bourdon had ever built. They called it Fritz. The name, according to one account, came from a machinist at the Krupp works who was said to have such perfect control of the machine that he could operate it like a surgical instrument. Another account says it was named after Alfred Krupp's own son. Either way, the spectacle around it was deliberate. Krupp understood self-promotion the way Nasmyth understood showmanship, and he personally lobbied heads of state to visit his factory. The story goes that when Emperor William of Prussia toured the works in 1877, he placed his diamond-studded watch on the anvil beneath Fritz and told the machinist to keep working. Fritz brought the 50-ton hammer down around the watch without touching it. The emperor was so impressed that he gave Fritz the watch as a gift. Whether every detail of that story is true is hard to say. But the hammer itself was real, and its 50-ton striking force made it the heaviest-hitting steam hammer on Earth for the next 16 years. Photographs from the period show Fritz in operation, a colossal machine surrounded by dozens of workers in heavy protective clothing, dwarfed by the sheer scale of the device they were operating. The Schneider company at Le Creusot watched what Krupp was doing and decided to respond. They had been building steam hammers since Bourdon's original in 1840. Between 1843 and 1867, Schneider and Company built 110 steam hammers of all different sizes, 26 of which they kept for their own factory floor. But as the demands of industry grew, as the cannon barrels got longer and the ship armor got thicker and the engine shafts got heavier, the hammers had to grow with them. And in 1877, Schneider finished building something that made everything before it look like a toy. The Creusot steam hammer could deliver a blow of up to 100 tons. Its steam cylinder stood 6 meters tall, with an inside diameter of 1.9 meters. Steam pressure, averaging 5 kilograms per square centimeter, drove the piston upward through 2 balanced single-acting slide valves, and then the hammer would fall under gravity to deliver its blow. The piston had a stroke of 5 meters, meaning the hammerhead could travel 5 meters from the top of its arc to the anvil below. And that anvil weighed 750 tons. It sat on a bed of oak timbers 1 meter thick, which sat on solid masonry, which sat directly on the bedrock beneath the factory floor. You could not build this machine on any random patch of ground. You had to anchor it to the planet itself. 4 separate steam furnaces fed the cylinder. The whole assembly was so massive that the factory had to be constructed around it rather than the other way around. The Creusot hammer eclipsed Krupp's Fritz overnight. 100 tons versus 50. The French had doubled the Germans, and they wanted the world to know it. In 1878, Schneider built a full-scale wooden replica of the Creusot hammer and displayed it at the Paris Universal Exposition. Visitors from across Europe and America came to stare at this monument to industrial force. But the hammer was not just about raw power. Like Nasmyth's original, like Fritz at Krupp, the Creusot hammer could also perform feats of absurd precision. Public demonstrations showed the machine corking a bottle without breaking the glass, cracking a nutshell without damaging the nut inside, and tapping a watch crystal without leaving a scratch. A 100-ton machine performing the work of a jeweler. The crowd loved it. Engineers across the world took notice. The Creusot hammer held its title as the hardest-hitting steam hammer in the world for 14 years. And then America entered the race. In 1889, the Bethlehem Iron Company in South Bethlehem, Pennsylvania, began construction on a steam hammer designed to surpass even the Creusot monster. Bethlehem had purchased patent rights directly from Schneider and built a hammer of nearly identical design, but scaled up even further. When the Bethlehem hammer was completed on the 3rd of June, 1891, it stood 90 feet tall and could deliver 125 tons of force with a single blow. Nothing on earth hit harder. The reason Bethlehem needed that kind of force was specific and urgent. The United States Navy was building its first generation of modern steel battleships, and those ships needed armor plate and massive gun barrels forged from solid steel. Bethlehem Iron had secured the contracts, and the hammer was the tool that made them possible. When the hammer was in operation, the vibrations traveled through the ground beneath South Bethlehem and into the surrounding neighborhoods, rattling dishes in kitchen cupboards across the entire town. At the 1893 World's Columbian Exposition in Chicago, Bethlehem built a full-scale wooden model of their hammer and displayed it in the main hall. A contemporary account described it straddling the central aisle like the Colossus of Rhodes, towering 91 feet to the roof beams, surrounded by models and sectional plans of the warships whose armor it had forged. The wood and plaster construction was so convincing that visitors thought they were looking at solid iron. The Bethlehem Works became the finest steel forging plant in the world, capable of producing armor plate and gun barrels for battleships of any tonnage that had been designed up to that point. From that forge in South Bethlehem came the components for the Great White Fleet, the steel warships that shattered the remains of Spain's colonial empire in the Spanish-American War of 1898 and announced the arrival of the United States as a global naval power. 12-inch gun barrels weighing 66 tons, armor plates thick enough to deflect anything an enemy could fire, crankshafts, and piston rods for the engines that drove these ships across oceans. All of it shaped under the falling weight of a steam hammer, descended from a sketch a Scottish engineer had drawn in a notebook 52 years earlier. The hammer that built those ships was, in a very real sense, the tool that forged a new world order. But the age of the steam hammer was already ending, even as the Bethlehem machine was still pounding away. Engineers had discovered that a hydraulic press, which applies steady, continuous force rather than repeated blows, could produce forgings that were more uniform and structurally superior to anything a hammer could make. The constant pressure squeezed the metal evenly in all directions, eliminating the internal stresses and inconsistencies that come from repeated impacts. By 1892, just 1 year after the Bethlehem hammer went into service, the company installed a 14,000-ton hydraulic forging press right next to it. The press produced better results. It was quieter, it did not shake the neighborhood. And over the following decades, hydraulic and mechanical presses got bigger and better, while steam hammers stayed more or less where they were. A modern hydraulic forging press can apply about 80,000 tons of force, compared to the 100-ton blow of the Creusot hammer. The technology simply left the steam hammer behind. The giant American hammer at Bethlehem, the 125-ton machine that had once been the largest in the world, was demolished by 1902. It had served for barely 11 years, but the Creusot hammer proved far more stubborn. It stayed in continuous operation for 54 years, forging iron and steel shafts, piston rods, and heavy components until its retirement in 1930. When it finally stopped, the factory that had been built around it eventually crumbled away. In 1969, the hammer was disassembled and rebuilt in the town square of Le Creusot, where it stands today as a monument. In 1981, the American Society of Mechanical Engineers designated it an International Historic Mechanical Engineering Landmark. If you visit the small French town of Le Creusot today, the hammer is still the main attraction, rising above the streets of a town that was once the beating heart of European heavy industry. A smaller Nasmyth hammer stands outside the old Patricroft factory site near Manchester, where the Bridgewater Foundry once hummed with 400 workers and the sound of metal on metal. A larger Nasmyth and Wilson steam hammer sits on the campus of the University of Bolton, and another stands near the pier at Wigan. One of Nasmyth's own hammers, built sometime between 1851 and 1856, traveled across the Atlantic and now belongs to the Smithsonian Institution in Washington. It was originally gifted by the Museum of Science and Industry in 1962. And then there is the man himself. James Nasmyth retired from business in 1856 at the age of 48. He sold his shares in the Bridgewater Foundry, packed up, and moved to a property in Penshurst, Kent, which he renamed Hammerfield. His reason for retiring was characteristically blunt. He said he had enough of this world's goods, and that younger men should have their chance. He was 48 years old, wealthy beyond anything his painter father could have imagined, and he was done with industry. But he was not done with precision. Nasmyth had built his first telescope back in 1827, when he was still a teenager in Edinburgh, grinding a specular mirror for a 6-inch reflector. Now, with unlimited time and money, he threw himself into astronomy the way he had once thrown himself into machine tools. He constructed a 20-inch reflecting telescope and, in the process, invented a new telescope design called the Nasmyth focus, which directed the light path through the altitude bearing of the mount so the observer could sit comfortably instead of climbing a dangerous ladder in the dark. He spent years making meticulous observations of the moon, building plaster relief models of the lunar surface from his drawings because photography was not yet advanced enough to capture the detail he wanted. He co-wrote a book called The Moon, considered as a planet, a world, and a satellite. He even studied the sun, observing what he called a willow leaf pattern on its surface that the astronomer John Herschel called a most wonderful discovery. At the Great Exhibition of 1851, 5 years before his retirement, Nasmyth's steam hammer had been displayed alongside his prize-winning maps of the lunar surface. The same man, the same hands. The same obsession with precision, applied first to metal and then to light. He died on the 7th of May, 1890, at the age of 81. By then, the Creusot hammer was already 21 years into its 54-year service life. Fritz was still standing at the Krupp works in Essen, and the Bethlehem hammer was a year away from completion. The machines Nasmyth had set in motion were still shaping the world, long after the man who first sketched one in a notebook had put down his tools and picked up a telescope. Steam hammers are not entirely gone, even now. Compressed air power hammers, direct descendants of the early steam hammers, are still manufactured and still used by forgers and metalworkers who need the specific kind of impact that a press cannot replicate. Wherever there is a pile being driven into the ground for a foundation, some form of a hammer derived from Nasmyth's 1845 design is doing the work. The technology shrank and adapted rather than disappearing completely. But what the steam hammer truly left behind is not any single machine. It is the principle that precision and power are not opposites. Before Nasmyth's sketch in 1839, the world understood force as something crude, something you aimed in the general direction of the problem and hoped for the best. After the steam hammer, force became something you could dial, calibrate, and direct with the accuracy of a watchmaker. That idea, the idea that you can hit hard and hit exactly where you mean to, spread outward from those Victorian factory floors into every branch of manufacturing, construction, and engineering that followed. The steam hammer did not just forge metal, it forged the assumption that sits beneath everything we build today. If this story surprised you, hit subscribe and drop a comment with the piece of industrial history you think deserves its own video. And if you got something out of this one, a like goes a long way in helping more people find it.